Hello everyone, my name is Chaya Trihan. I'm a PhD student at London School of Economics. Today I'll talk about computing approximate shortest paths in dynamic streams. This is joint work with Mikhail Elkin from Ben Gurion University. Computing shortest paths in graphs is a fundamental graph theoretical problem. A lot of research has gone into solving this problem in various models of computation, such as sequential, distributed, parallel, and streaming. In this work, we focus on the streaming model of computation. In the streaming model, the vertices of the graph are known to the algorithm and edges are revealed one at a time. And if the stream is static, an edge can only be added into the graph, and once inserted, an edge remains in the graph forever. On the other hand, if the stream is dynamic, edges can be added as well as deleted as the stream progresses, and the stream arrives as a sequence of updates where each update is a tuple of the form E sign, where E is the edge being updated, and E sign takes a value of +1 if the edge is being added, and it takes a value of -1 if the edge is being deleted. In addition, if the input graph is weighted, then we have a third entry in the tuple, which is the weight of the edge being updated. Now, typically, one is allowed to make multiple passes through the stream, and it is desired that the graph streaming algorithm should solve the problem at hand by using space which is sublinear in the number of edges and by making a small, preferably a constant number of passes through the stream. Now, to solve the problem, we build structures such as spanners and hopsets. So I'll go over the definitions of these structures. So given an input graph G equal to VE and two parameters alpha greater than 1 and beta positive, a spanner H of G is a subgraph, or essentially a subset of edges of G, such that for any pair of vertices U and V, the distance between them in H is at most alpha times the distance between them in U and V plus beta, and alpha beta together constitute the stretch of the spanner. When beta is 0, we have a multiplicative spanner, and when alpha is 1, we have an additive spanner. The fundamental trade-off in the design of a spanner is between its stretch and size or the sparsity. So for example, for large distances, an additive stretch is much better than the multiplicative stretch, but purely additive spanners are not always sparse. So in 2001, Elkin and Peleg found a sweet spot between the two extremes of multiplicative spanners and additive spanners by showing the existence of sparse spanners for which the multiplicative stretch alpha can be made arbitrarily close to 1 while keeping the additive stretch constant. These are called near additive spanners, and this is what we build for unweighted graphs. In the case of weighted graphs, things get a little more complicated because in a weighted graph, the length of a path is not measured in terms of the number of edges on the path, but by adding the weights of the edges on the path. So it could be that there is a pair of vertices U and V which are very close to each other on the graph, but the shortest path between U and V may involve a lot of edges, and any distance exploration on the graph in this case may involve going over a lot of edges. We circumvent this problem by building a structure called hopset. So we are given a weighted input graph G, and we augment this weighted input graph G by adding to it weighted shortcut edges to obtain another graph G prime, such that for any pair of vertices U and V, we can go between them in G prime by taking a path which contains at most beta edges. Moreover, this path in G prime, which contains at most beta edges, the length of this path is at most 1 plus epsilon times the length of the shortest path between U and V in G. Here, beta is called the hop bound of our hop set, and 1 plus epsilon is the stretch of our hop set. And this is the structure we build for weighted graphs. So for the problem of computing shortest paths in dynamic streams, so far two types of solutions are known. So the first type of solutions, they first build a multiplicative spanner with stretch to kappa minus 1, and then size order n to the 1 plus 1 over kappa by making kappa passes through the stream. And then the shortest paths are computed in the spanner offline. So sometimes one can actually trade off the number of passes with the stretch. That is, by allowing higher stretch, we can reduce the number of passes, but the trade-off remains. The problem with this approach is that it is doomed to incur a stretch of 4 kappa by 3 due to an existing lower bound. Moreover, when the graph is weighted, one incurs additional multiplicative stretch of 1 plus epsilon. And now the other type of solution for this problem computes an exact single source shortest paths tree, but that employs a lot of passes. In contrast, in our work, we give the first dynamic streaming algorithm for single source shortest paths with stretch 1 plus epsilon space order n to the 1 plus 1 over kappa by making a constant number of passes when the graph is weighted and a polylogarithmic in n number of passes when the graph is weighted. Moreover, within the same complexity bounds, we can compute approximate shortest paths from a set S of source vertices as long as the size of the set S is at most n to the 1 over kappa. Notice that our multiplicative stretch 1 plus epsilon is much better than 2 kappa minus 1. And as a byproduct, for building the structures such as spanners and hopsets, we give a sampling technique which can be used as a general purpose L0 sampler for sampling uniformly from the support of a vector. So in our spanner, as well as our hopset construction, we use the technique of superclustering and interconnection, which was originally devised by Elkin and Peleg. In the superclustering and interconnection approach, the algorithm proceeds in phases. In each phase, the input is a set of vertex disjoint clusters, each with a designated center. In the first phase, each vertex is a cluster in itself. And in the phase I, our goal is to interconnect all the nearby clusters which are within distance delta I from each other. We interconnect the clusters by adding shortest paths between the respective centers or by adding weighted edges between the centers in case of hopsets. So this gives us good stretch. But the problem with this approach is that if a cluster is very popular, that is, it is within distance delta I from a lot of other clusters, we may end up adding a lot of edges. Okay, so which is not good. So in each phase, the step of interconnecting nearby clusters is preceded by what we call a superclustering step. In the superclustering step, each cluster or cluster center is sampled with probability 1 over deg I, where deg I is an appropriately chosen degree threshold. Now, from the set of sampled centers, we build what we call superclusters. So every sampled center does a distance exploration, and then it actually superclusters all the nearby clusters into itself. So the idea is that if a cluster is very popular, in our case, let's say C2 is very popular because it's close to a lot of other clusters, then one of its nearby clusters, in this case C3, will get sampled and then create a supercluster and supercluster the popular cluster into itself. Now this game between stretch and sparsity goes on for a few phases until we are left with a very few clusters which we can simply interconnect. Okay, so this is superclustering and interconnection approach. Okay, so to implement superclustering and interconnection, in the dynamic streams, we solve the following problems. For superclustering, we give a subroutine for performing a BFS exploration in unweighted graphs and an approximate Bellman-Ford exploration in weighted graphs up to a certain depth, let's say eta, from a chosen set of source vertices in eta passes. And for interconnection, we give a subroutine for performing multiple simultaneous BFS explorations, or in the case of weighted graphs, approximate Bellman-Ford explorations up to certain depth eta from a set of starting vertices in eta passes. Now, between superclustering and interconnection, superclustering is relatively easy. We have to perform just one shallow BFS or Bellman-Ford exploration, which can be done. The real challenge is in implementing the interconnection, because we have to perform multiple simultaneous BFS explorations, which can blow up the space usage. Now, during the interconnection, if the stream was simply static or insertion only stream, there were no deletions, then we can actually use the following fact to our advantage. It is that every vertex V in V is part of at most order Degay log and distance explorations during the interconnection. Now, this is a byproduct of preceding every interconnection step by a superclustering step. Okay. And this is very good for static streams, because in a static stream, when an edge appears on the stream, which is on a shortest path to the source of one of the explorations, we can simply safely store the edge, because we know there will not be many of them, so you can store all such edges. Now, in the case of dynamic streams, this is not good, because of edge deletions. For every vertex V in V, we may appear to be on a lot more explorations as the stream progresses than it finally ends up belonging to when the stream ends. Okay. So when we see an edge on the stream which seems to take us to one of the exploration sources, we cannot simply store that edge. Okay, to solve this problem, now we cannot do simply store. To solve this problem, this is what we do. For every vertex V in V, we use a sampling technique which helps us extract the set S of explorations that V is a part of. Okay. So once we have extracted the set S, then for every vertex V in V, we sample an edge on the path to the root S of every exploration that V is a part of. Okay. Now I'll give a very quick overview of our sampling technique, which can also be used as a general purpose once-pass recovery or L0 sampler for strict turnstile setting. Okay, so we will take the simplest case. We consider a vector A which has entries A1, A2 up to A of AN, and support of A is, which is the number of non-zero entries in A, is at most K. So for the demonstration purposes, we assume that the vector that we are considering, its support is at most 1. Okay, that is K is 1. Okay, now this vector A is presented to us as a sequence of updates where each update is a tuple of the form I delta AI, where I is the coordinate of the vector which is to be updated, and delta AI is the amount or the value by which the coordinate I has to be updated. It can be positive as well as negative. We assume that at the end of the stream, the final value of each coordinate is positive. That is, we are in the strict turnstile setting. So the final value of coordinate I, AI, is the sum of all the updates that we have seen to the coordinate I through the stream. Okay. So this is how our sampling technique works. We are presented a vector A as a sequence of updates. So first thing we do is we use an encoding scheme, new. So this is how it works. So we have a set C, which is a set of convexly independent integer vectors in Z2. Okay. So now we map each coordinate I of the vector A to a unique point in C. Okay. Now we maintain two things as the stream progresses. One is an integer vector L and one is a integer counter CTR. So L is initially a 0 vector and counter CTR is 0. So as the stream progresses, we update our integer vector L with encoding of the coordinate I times the amount or the value by which the coordinate I is being updated. Okay, and we update the value of the counter CTR by the value by which the coordinate I is being updated. Okay, so notice that as the stream progresses, at every intermediate point, the value of L is a linear combination of the encodings of the certain coordinates. Okay. Now, when the stream stops, what we do is we take L and CTR and we just divide L by CTR to get L prime. Okay. So L prime, if you see, is a convex combination of all the I's we have seen. Now, then we check if L prime maps to some new I, okay, for some I, okay. So recall that our set C, from which each coordinate gets its encoding, is a set of convexly independent points. So if L prime maps to new I for some I, then we know that no new I can be written as a convex combination of encodings of other I's. So that means there is only one coordinate in our final L value of L prime, and we return I as the coordinate which we have extracted, and the value of AI is CTR. Okay, now if to see how our one sparse recovery routine that we just defined works against a known one sparse recovery routine by Ganguly, which also works in turnstile streaming setting, we see this table. So the space complexity of our thing as well as of Ganguly is order log n. But in case of Ganguly, the processing time per update is order 1, and in our case, it is polylog n. But in our case, in case of graphs, it is order 1 because we can pre-compute the encodings of all the vertices, because vertices of the graph are known to the algorithm. So we don't need to recompute encoding every time we see an update. Okay. So with the encoding scheme and sampling in place, we can build spanners and offsets. Okay, so in unweighted graphs, this is how we compute the approximate shortest paths once we have the spanner. So first we build a near additive spanner. Then in the spanner, we perform an order beta over epsilon BFS exploration from each source. For each pair S and V in S cross V, which are within distance beta over epsilon, we get the exact distance. If there is a pair SV in S cross V, which is further away, then the additive stretch that we get is subsumed in the multiplicative stretch, and we get a multiplicative stretch of 1 plus order of epsilon. Okay, in the case of weighted graphs, things are a bit complicated. Okay, so in the case of weighted graphs, we assume that the minimum distance between any pair of vertices is 1 and the maximum distance is lambda. Okay, now this is the range of distances that you can see on the graph. So we divide the range of distances into sub-ranges, okay, on a geometric scale, 1 to 2, 2 to 2 to 2 square, and so on, and up to 2 to the log of lambda minus 1 to 2 to the log of lambda. Notice that now for each of these distance subranges, we build a separate hop set, okay, using superclustering and interconnection. Notice that we don't need to actually compute up hop set for distances up to beta. This is because for any pair of vertices which are within distance beta or to each other, there is already a path which contains at most beta hops in the original graph. So we start building hop sets from the scale log of beta. Okay, now remember we are doing Bellman-Ford explorations in superclustering as well as interconnection. Okay, so and some exploration may take up to order and depth. Okay, so which is not good because that means we'll have to do order n passes through the stream. So to avoid that, instead of building all these hop sets in parallel, we build hop sets one after the other. So when we build a hop set for the distance subrange 2 to the k, 2 to the k plus 1, we actually use hop set edges from the hop sets at lower scales, and this actually makes sure that every time we compute a hop set, we actually do not go to a depth beyond order beta. Okay, so with this, we have computed all these hop sets and one after the other, and they give us 1 plus epsilon approximate distances. Now the problem is that here hop set size, hop bound, space, and number of passes, everything depends upon lambda. So in the extended version of the paper, we actually eliminate the dependence on size, hop bound, and number of passes. And our space complexity still mildly depends on lambda, but that is also the case for all the solutions which are based on multiplicative spanners. So finally, how we compute approximate shortest paths in weighted graphs. Once we have the hop sets, we perform an approximate Bellman-Ford exploration up to depth beta, and we know that we can go all the distances can be approximated by a multiplicative stretch of 1 plus epsilon within beta hops, so we are good. Okay. So finally, to conclude, we have given algorithms for approximate shortest paths in dynamic streams with best stretch known so far. We have given constructions for near additive spanners in dynamic streams, near exact hop sets in dynamic streams, and we gave a sampling technique for once pass recovery and L0 sampling in strict turnstile setting, which may be of independent interest, although our sampling technique is slightly inferior because it works only in strictly turnstile setting. But we believe it's of independent interest. An interesting open problem is that the problem of computing 1 plus epsilon approximate shortest paths in constant number of passes is not done in weighted graphs. Remember, in the case of weighted graphs, the number of passes is polylogarithmic in n. So computing 1 plus epsilon approximate shortest paths in weighted graphs in constant number of passes is still open. Thanks for your attention.